Hi everyone and welcome to this theory lecture. Today we are going to see a very important theorem that will be useful for our next discussions, especially contour integrals. And this theorem is called the residue theorem. And it says that if you have a function and that function is defined in some domain, or let's say in some region, and you want to evaluate the integration of this function along some contours, and inside that contour, let's say there are some singularities, that means points that are singular, and if you do that, this will be just 2 pi I times the summation of the residues. So let me draw a picture so that it's a bit better to understand. Let's say this is the contour and you are going around the, obviously a simply connected contour, and you are going around the contour in a counterclockwise sense. Some f of z is defined in this region, but there are some singular points. Okay, let me just use the cross mark to let you know that these are the singular points. So this cross means singularities. So the theorem says that whenever you evaluate this contour integral for this f of z, where these x's are singularities, obviously you have to keep in mind that these singularities are inside the contour, not on it, and at the same time the number of singular points should be finite. So the number of singular points is finite, and this is what the theorem tells us, that you evaluate the integral around this contour and you get this result. So I'll just try to draw a very informal proof of it. So this is the proof, and you know from your Taylor and Lorentz series experience, or let's say from knowledge, that this f of z can be written as a Lorentz series and around any of the singular points, right? So let us just consider only one singular point. Let's say I'm considering this one, only one, and obviously I need to write that over here. So let's consider we are, okay, let's call it A. We are dealing with only one of the singular points. That means I'm choosing a contour like this circle, that almost circle looking thing, and this only encloses one of the singular points but not the others. So this is, let's say, some contour C, and you know from Lorentz series that around this singular point the function f of z can be written as this: a of n z minus z naught to the power n, and this is just the Lorentz series expansion. And now what you're going to do, let's say the singular point is z naught. So this point A is our z naught point. That means it has some value. Let's say the origin is somewhere over here. This is the origin on the Argand diagram, and this is z naught. So you can easily recognize that this circle will have a parameterization like this: z minus z naught is equals to some rho e to the power I theta, where rho is the radius of the circle, which is obviously very small. And since we are considering an integral like this, f of z dz, we need to find this dz as well, right? So this dz will be just I rho e to the power I theta d theta. And since this is a circle, that means it's a closed contour, and by even if you don't consider it as a circle, you consider something like this around this singular point, you can deform the contour and make it a circle. This is already familiar to you via the theory of deformation of contours. So that's why I chose a circle in the first place, but again, you can choose any contour you like, and as long as you don't hit a pole, you can deform the contour and make it a circle. Sorry for that. So now you just put these things inside this integral, right? And here, instead of f of z, you need to use this series formula. So let's try to do the integral right now. That this is, oops. F of z dz. This can be written as the summation, and the integral is over here from 0 to 2 pi. The summation is over from n is equals to minus m to infinity a n z minus z naught to the power n, and then we have our dz, right? Also, I'm going to assume that this singular point is a pole and it has an order of m, because if you recall from your Lorentz series expansion that the highest order, the lowest order, that is the starting point, is just the order of the pole itself. So that's why I'm assuming that this z naught has an order of m. And now we are going to use the parameterization that came from this line. So let's put these things up, and what we're going to do now is that we're going to flip this summation and the integral symbol, because integral itself is a linear operator, so we can do that. However, there are some subtleties, and the subtlety arises when the result is not finite. Since we are expecting the result to be finite, that's why we can flip this operator as well. But if you don't like the idea that I just shared right now, you can just forget about it, the finiteness of this thing, and you can say that since this is a summation and this is a integral is a linear operator, so you can flip them like this. So 0 to 2 pi. Obviously we're going to pull a n out because these are the coefficients, just constants and stuff, and this will be just I rho to the power n plus 1, and there will be e to the power I n plus 1 theta, and there will be this d theta thing. Now this seems pretty straightforward, and before I carry out the integration, what I would like to do is that I want to decompose this series into two parts. That is a series where n won't be equals to 1 and a series where n will be equals to 1, because if you see, the summation is running from n is equals to minus m to infinity, right? So this can be broken down like this minus m to infinity. However, you put another condition that n is not equals to 1, another one, and since n is not equals to minus 1, not 1, n is not equals to minus 1, and since you are missing one term inside this summation, you have to add that term, that is the term corresponding to n is equals to minus 1 over here. So if you put n is equals to minus 1, this will be just, there is a term like this, and this is the term that comes from n equals to minus 1, right? Because again, this is running from minus m to infinity, but it doesn't contain the n is equals to minus 1 term, and that term is just over there. So this is the decomposition that I'm going to use right now. So let me just write this thing down. N is not equals to minus 1 to infinity, a of n 0 to 2 pi I rho n plus 1 e to the power I n plus 1, plus 1 theta d theta. Okay, so this is our side note, and when n is equals to 1, n is equals to minus 1, this is just a minus 1, integration of 0 to 2 pi, there is this I, rho minus 1 plus 1, e to the power I minus 1 plus 1, theta d theta, right? Now carry out the integration. So the integration will give us something like this, that is this integration over here. So if you carry out this integration, you will have something like this. Summation over n is equals to minus m to infinity, where n is not equals to 1. There is this a of n, and I carry out the integration, and this is just I rho to the power n plus 1. Now let me just write exp instead of e because there will be more terms. So this is the most convenient format. So theta divided by I into n plus 1, and the limit is from 0 to 2 pi, right? And the second part, that is this part, will just contribute a minus 1, and there will be a I and a 2 pi, because you see that rho to the power minus 1 plus 1 is just rho to the power 0, that means it's 1. Similarly for this term over, this will be 1. So this integral will ultimately be just a inverse 1 I 0 to 2 pi of d theta. So that's where this 2 pi is coming from. Now notice this part. If you put the limits for theta, you see that this part is just 0. So finally what you have is a minus 1 I and a 2 pi. But this a minus 1 is what? This is the residue, right? So ultimately you have this 2 pi I times the residue for the point z0. Okay, so ultimately you can write f of z dz is equals to 2 pi I times the residue of z0. That means this is a residue for the singularity z0 or a pole. Now you might ask that this is only for one of the points, right? But what happens when there are other points? That means you are considering this full contour right now, this full contour like this, and now you're enclosing a lot of points like this. So how does that work out? So I won't show you the most rigorous proof, but I can show you more of a graphical proof that will look something like this. Let's say your function has 3 singular points. Obviously it should be finite, or let's say 4 like this, and the contour that you are thinking is something like this. But you can deform the contour and make things look like this as well. And now what will happen is that there are 4 points or 4 singularities. So in your Lorentz series expansion, you have to consider all 4 of these points, and instead of a residue coming from a single point, now you have to add the residues of all these 4 points. So that's where this idea comes in, that it will be just, if you do that in a more rigorous manner, you will see that this is just the 2 pi I plus sum of the residues. And this is the theorem. Even if you don't understand the proof, don't worry. This is the theorem you need to keep in your mind to deal with the following discussions that will appear later. And this is the central theorem of evaluating contour integrals. So this will be it for today, and I'll see you guys on the next lecture. Thank you.